This is physics for week 11. Excuse me if the handwriting is bad or the quality is bad, just bear with me for this week, just this week. The more turns a galvanometer coil has, the less sensitive it is. Actually, this is the opposite, as the more turns means the more sensitivity. A galvanometer loop must be placed in a radial magnetic field. This is always, you should always do that. The magnetic field induces the torque on the current carrying coil of a galvanometer. Yes, the coil of a more sensitive galvanometer contains a spring with a smaller constant. Here it is. Here it is. It's in the book. Please, 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 I advise to read the book before doing the quiz. It's very, very beneficial. It won't take 5 minutes from your time. Obviously, let's check the last option. The greater magnetic field a galvanometer is placed into, the less sensitive it is. Should be also more sensitive, as it's directly proportional. So the more turns with a greater magnetic field should be a more sensitive galvanometer. Question 2. This was in previous AMSs, so if you want to check it out quickly. Next. Okay. Describe an electric field. As we know, there was a formula from before. Let's just read first. Magnetic, it's a magnitude and direction, yes, so it's a vector quantity. Magnitude of an electric field is a force over charge, so it's a force. As we know, it's a force over Q naught. That was a formula in, I think, chapter 2. It's equal to the electric field. Okay. And then it's a scalar quantity, obviously not, because we said it has a magnitude and direction, which means it's a vector quantity. It is best described using charged spheres, not always. The magnitude of the field at any point is work per unit charge. It is not work, but perhaps it's the force per unit charge. Next. This was in previous AMSs as well, but let's read it. A magnetic field B makes an angle theta with the square-shaped elastic frame of side L. They want to double the magnetic flux. How do we double the magnetic flux? You need to double the magnetic field. You can double the magnetic field, or double the area, or double the cosine of the angle. You don't double the angle, but you double the cosine of the angle, and not the sine. Why not the sine? Because here, if you're gonna draw it like this, okay, and then let's say it's tilted like this, making an angle theta. Obviously, the only thing that's passing to it, it's this one. So it's BA cosine theta itself. Okay. So that's that. Question 5. Okay. Which of the following are true about the energy transformations in an electric DC motor? Select all that apply. The energy of the DC motor is the energy of the magnetic field. Wrong. It's the energy of the battery. So yes, the energy of the battery, as we said. Whenever a DC motor is on, but it's prevented from moving, okay, most energy is transformed into heat. This is true. What they're trying to say here is, when you have a DC motor, okay, a DC motor looks something like this. I think I have it. Something like this, okay? When you have a DC motor and you prevent the electric charges from moving in the motor by, let's say, by blocking their path somehow, actually almost all the energy is transformed into heat, which is very, very dangerous. So if it comes in the exam, it's a very, very dangerous process. An electric motor loses some of its energy due to resistance in the coil, yes. And then the efficiency is always 100%, nothing is always 100%. Why is it not 100%? Because there is obviously resistance due to heat. The diagram below shows a wire carrying a current directed rightwards, placed in a magnetic field directed inside the plane of the picture. The electromagnetic force exerted by the magnetic field on the current is directed how? To do this, we know that the magnetic field, they're telling you it's into the page. Okay? They told you the current is rightward. And then they told you, so, okay, let me just try to do it. Yes, it's correct. They told you here that the current is rightward, correct? Nice. Then we know that with the IBF rule, your thumb, sorry for the handwriting, your thumb is the current, your index finger is the magnetic field, denoted B, and your middle finger, I'm just gonna say it mid finger, is the force. Okay, I'm sorry I do not have a camera to perform this and show you guys this. Excuse me for this. So we know that the current is to the right, so you point your thumb how to the right. Point your right thumb to the right. This is called the right hand rule. So you point your right thumb to the right. Then they told you the magnetic field is into the page. You need to know that when it's across, so it goes into the page. So you go with your thumb to the right. With the magnetic field is into the page, so you point your index finger, which is your first finger, into your screen, and then you just you extend your three fingers or your middle finger, depending on how you do it, doesn't matter. You extend your last three fingers, and then you just check. If you extend your last three fingers with your thumb pointing rightward and your index pointing into the plane, you will notice that the magnetic field, the electromagnetic force is pointing upward. Next. Okay, as we said here that this device is the DC electric motor, as I showed you. So this is DC electric motor. Side A experiences an upward magnetic force. I think I had it here. Okay, just know that it turns like this. Okay, turns in a counterclockwise manner. Next. Okay, this is some great questions. In the experiments, when objects are charged by rubbing, objects that behave like polythene are negatively charged, and that behave like glass are positively charged. This is all from the grid. Please read the grid that Mr. Hani specified here. Another term for earthing a conductor is grounding the conductor. In the process, the conductor is connected to a much bigger conductor. Again, this is grid. Moving on. Again, another great question. Objects become charged when they gain or lose electrons. Objects can only gain or lose electrons. You can't gain or lose protons. Electrons have a negative charge, protons positive charge. Object that gains an electron acquires a negative charge. Next, number 11. Okay, the electroscope shown below was positively charged by a glass rod. So the electroscope, this entire thing is positively charged. The glass rod of the gold leaves of the electroscope, which are these, spread away from each other. It's logical because the whole thing is positive, so this positive, this positive. Okay. When another charged rod W is brought close to the metal knob, the gold leaf comes closer together. What is the charge on W? Obviously, since they were first repelling, if they come close, that means they attracted. So this has to be something that attracts the positive charges. What attracts the positive charges? The negative. A negative charge. And you need to know that it's something that just it's here, that an increase in the divergence of the gold leaf shows that an object has the same charge as the electroscope. Okay, moving on. Okay, which of the following can be referred to as an electric current? A flow of positive charges, of course. Flow of neutral atoms, never. Flow of negative charges, yes. Random motion of negative charges, it's not random. It's a flow. Okay, so this is wrong. And then a random motion of neutral atoms, we said neutral is always incorrect. Moving on. Again, this is good. What does the thermocouple measure? It measures temperature. W and Y, they measure, they are made of the same material, sorry. X measures the current. X is actually a galvanometer. Okay. X is a galvanometer, and wire W, where is it? Wire W, I'm actually not sure. I'm not sure what does each one measure, but that's how it is. Thermocouple has a low heat capacity and relatively high precision, not high heat capacity. Can measure only high temperature, no. Have a slow response to temperature changes. Everything is here, sorry. Thermocouple have a low heat capacity, makes them respond quickly. They said here does not slow response, that's why it's wrong. Changes in temperature, and moreover thermocouple very sensitive, and they have a high precision. Moving on, a polythene rod is rubbed against a woolen cloth. The rod gains negative charge as shown below. If the rod gains negative charge, that means the woolen cloth is positive. So the charge required by the woolen cloth is positive. If the cloth and the rod are brought close to each other, they attract, because this is positive, this is negative, they attract. Okay. For questions like these, you should know that it always goes out of the positive into the negative, out of the north into the south. Okay? So let's see, particle S is positive. Why? Because it's going out of S into T, so T must be negative, as we said, yes. U it's going out, so it's a positive. V is also going out, so V is also positive. Moving on. Here, this is a very simple question. You just do, as we know, 150 plus 273 by now, 423.15 if you want. Okay, the force between two equal charges that are 2 centimeters apart is 1.2 millinewton. If the distance between the charges decreased 0.5 to 0.5 centimeter, the force then becomes, okay, we need to find the force. We know that F equal K Q1 Q2 over R squared. So therefore, we know that F is directly proportional to 1 over R squared, which means that they're actually inversely proportional. Okay? That means that F1 R1 squared equal F2 R2 squared. Applying it, you get 1.2 times 2 squared equal F2, which is, we don't know it, F2 times 0.5 squared. So it's, let's actually do it on the calculator. So it's, we do 1.2 times 2 squared over 0.5 squared, 19.2, which is actually 19.2, the answer. Okay? So that's how to do that question. Next. A neutral conducting sphere suspended by a thread is brought closely to a positively charged rod. Obviously, the sphere will be attracted by the rod as it's neutral. Anything neutral, insulating, neutral, conducting, whatever, it attracts. Next. Okay. A current carrying a wire segment is parallel to the ground. The current flows inside the plane of protection. They told you again, they helped you. They told you the current is flowing into the plane. You need to read this very carefully, because like they may tell you the current, they may tell you the magnetic field. So please read this very, very carefully. I'm telling you the current is flowing inside the plane. In order for the magnetic force to compensate the weight, a magnetic field should be directed leftward. Okay. A magnetic field should be directed leftward. Obviously, you need the IBF rule. So let me write it IBF. Always the right hand rule. The I, you draw it in, so the I is your thumb, and you do it into the page. So let me just write thumb. So you put your thumb into the page. Then they're telling you to compensate the weight. So the weight is obviously vertically downward. So to compensate it, you're gonna point the force upward. So it's gonna be up. Your last 3 fingers, and then your magnetic field, which we're trying to find. So do it now. The current, if you point your finger inwards, if you point your thumb inwards, and then if you point the force upward, immediately you should notice that the magnetic field points leftwards. The 3 rules, sorry, that to determine the force is the right hand rule, motor force rule, right hand screwdriver rule. Next, again, they're saying you a current carrying wire is placed in a uniform magnetic field as shown below experiences a force 20 millinewton. The force exerted on it should be to the right. Why? Let's check. They told you the current is inward, magnetic field upward. As you know, the current is the thumb, so you're gonna put your thumb pointing towards your screen. Your magnetic field, which is your index finger, upward, and then you immediately notice that your 3 last fingers are pointing towards the right, so the force is directed towards the right. If the current of the wire is doubled, the force becomes 40. You know, you should know that the current and the magnetic field are directly proportional to the force. So if the current is doubled, this 20 doubles. In order to make the force equal to 20 again, you need to read this again, very important, the magnetic field must be halved. So now it's 40. To make it 20 again, you need to halve the magnetic field, as magnetic field is directly proportional to the force, as well as the current is directly proportional to the force. This was in last week's AMS, we re-explain it now. They want to label the coil with the smallest flux as 1. Obviously, the one that's parallel is 1. Then, between 2 and 3. 2 is more closer to being flat. So that's why 2 is less than 3. It has a less flux than 3, and then 4 obviously has the greatest flux as it makes an angle of 90 degrees. In this question, I'm not really sure about it, but let's do it together. A current carrying loop is placed into a uniform magnetic field as shown in the diagram below. The loop will rotate to decrease the magnetic field entering its north face. You should know this, it will rotate to decrease the magnetic field entering the north face, and it will rotate to increase the magnetic flux entering the south face. I think I had it. 1 second. Yeah. So when a current carrying coil is placed in a magnetic field, magnetic forces will act on the coil in a way to increase the magnetic flux entering the south face. This would imply that the coil rotates clockwise. I'm actually not pretty sure about it, but let's maybe that the coil will rotate clockwise. Why? Because when we have the south, obviously south is like this, so it's clockwise. And we want it to we want the coil to rotate, so we make it clockwise. North goes like this, which is counterclockwise. I'm not really sure about this, so don't take my words for it. I'm not sure about part B. But excuse me on that one, I'm very sorry, but let's continue. The device shown is the galvanometer. It's in the book. The device is used to measure weak or sensitive currents. Let's read the. Okay, which of the following will make the device more sensitive? Select all that apply. Adding turns to the coil, yes. Stronger magnet, yes. Reversing the direction, no. Using a spring with a higher spring constant, no. We said, if you remember, a smaller spring constant here, smaller spring constant. And using coil with less turns, no. If you want, you can read this for yourself. This is very, very important. Memorize this. This is a split ring commutator. This is a brush, and the device shown is the DC electric motor. Electric DC motor. They're all the same thing, as I said here. Electric DC motor. Moving on. The diagram below shows a DC motor. The polarity of the magnets and the current as shown below. If the current is turned on when the coil is in the position shown in the diagram, the coil will rotate counterclockwise. As you remember, I told you it always turns like this. If it's south north, okay, yani look here. Here is south north, so it only turns like this. If it was rotated, so it's going to turn like this. So if the south was here, north was here, the thing rotates, and the brushes are made out of carbon. Last question. A current carrying rod is placed near a U-shaped magnet. Select two pictures in which the magnetic force has same direction. Obviously, look, you have the north, you have the south, and then the current is into the page. Which one of them will be the same? It's when you change it's when you swap it, and then it's like you flip the magnet. So when you flip it, this also the current flips. So like your right hand rule will flip, and the south and the north will flip. The current carrying rod in the diagram below has been moved closer to the north pole of the U-shaped magnet as shown below. The force on the rod in the new position will remain the same because the current is basically the same. Thank you for watching. Good luck tomorrow in the IELTS.